Hello and welcome to another USACO video. I know I haven't done USACO for a long time now, so it feels good to be back. But today we're going to do the 2025 February contest silver problem, the best lineup. Okay, so this problem is about a lineup as mentioned in the title, right? So essentially, we have n cows standing in a line, and each cow has an integer. And then Farmer John will create another line B in the following manner. So initially it's empty, and then while A is not empty, remove the cow at the front and maybe add that to the back of B. So as you can see, we're getting rid of some cows in line A, right? And we're just choosing some cows in line A and putting them in line B. And the thing we want to construct is the lexicographically greatest sequence of labels. So what does that mean? Well, I like to think of it as like a dictionary, right? So if I have a word after another word in a dictionary, it would be lexicographically greater than that word. So like um so obviously like banana would be after apple, so that means it would be lexicographically greater. And the interesting about lexicographically greater is that it looks at kind of like the first position where the current integer or letter is greater for the word, right? So it looks at the first position where it does that. So if I had something like 43321, right? And then I had something like 43311. Now the 433 is all the same, but 2 is greater than 1. So that means it's lexicographically greater. Okay, so just make another example. I have two sequences of numbers here. One is 711, one is 6998. Now, which one is lexicographically greater? Well, the 711 because 7 is greater than 6. And as you can see, right, the 1 1, both the 1 1s are smaller than the 9, 9, and 8 over here. But that doesn't matter. We only care about the first one that is greater, right? So this would be the lexicographically greater one. Okay, so back to the problem. What we need to do is create the lexicographically greater, but there's one more thing is that before we do that, we can choose a cow in line A and move it up in position before we do that. So that's interesting. Okay, so I'm going to come back to that. But first, I want to just take an example, right? So let's take this example. 5, 1, 2, 6, 3, 4. 5, 1, 2, 5, 1, 2, 6, 3, 4. So for this example, right? Let's just say we don't get to like move anything beforehand. So how do you create the lexicographically greatest? Well, the first thing you take is the 6 over here. So you would be cycling through like this. You would be looking through these numbers. But the first thing you need to take is 6. Why? Because 6 is the greatest here, right? If we take 6 and we just put it here, right? That's the best thing we can do. If we take 5, right? 5 is smaller than 6 and it's the first number that does that. So it's going to be lexicographically smaller. So we don't want that. We want the greatest. So we have to take 6, right? So all of these numbers we don't want. We go to 6. We take 6. Okay. Now after we take 6, do we want 3 or 4? Which one do we take? Well, we take the lexicographically greatest. So if we take 6, 4, that would be the greatest, right? That would be bigger than 6, 3, right? So we want to do that. So we don't take this and we take 4. Okay. Okay, that's great. Okay. So it seems like we just take like the greatest each time. So we just look through, we find the greatest, right? Okay, we take that and then we just look through and we find the greatest, right? Seems like that's what it is. Let's do another example. Let's do this one. 4, 3, 2, 1, 3. 4, 3, 4, 3, 2, 1, 3. Okay, so we're trying to take the greatest, and then we just keep going, and we just take the greatest each time. So we take 4. We take 4 because that's the greatest. Okay, now we look at 3. We can see that 3 is the greatest here, so we just take 3. Now, do we want to take 2? Well, we don't want to take 2 because later we're going to have 3, right? So we don't want to take 2 because later we can have 3, and 3 will be greater than 2. So we just ignore 2, and we ignore 1, and we take 3. So yes, this works, right? Taking the greatest each time always works. You're always gonna get the lexicographically greater sequence of number that you can construct here. Okay, so everything seems good. So now we go back to the condition that we were talking about before. Is that you can switch something, right? You can switch a number before you do this. So the question is, which number do you switch? Now for this example, it's pretty simple because you would obviously want to switch to 6 and put it to the front, right? Because now you can take it earlier, right? And what that allows you to do is that after you take the 6, you can take this 5 now, and 6, 5 will be greater. So let's try that, right? Let's try that. So 6, 5, 1, 2, 3, 4. So we swapped it like this. Now we have this. We do the same thing, right? Take the greatest. Take the greatest. Here is a 6. Go down the line. Now we have 5. That's the greatest. Take the 5. Okay, 1, 2, 3 are not the greatest. 4 is the greatest out of all of these. So we don't take this, and we just take 4. So before we had 6, 4. Now we have 6, 5, 4, right? And that's a much better sequence because 5 is greater than 4. And so this is the greatest possible sequence that you can make after swapping something, after moving something up. So it's okay. Let's just do the last example over here. 4, 1, 3, 2, 1, 1. 4, 1, 3, 2, 1, 1. So what are we trying to do here? We're trying to move something up, right? We're trying to move something up, and then we're gonna run the algorithm that we just mentioned here. So think about it. What should we move up? So if we just think like how we thought over here, right? Putting like the greatest up. Well, the greatest is already up, so we can't move it more up, right? So what should we do now? Well, we probably should put the second greatest up. You would probably think that we would do something like this. And okay, and then you would run for both of these, and you would find out that the biggest for this without putting it is gonna be 4, 3, 2, 1, 1. I just ran the algorithm. That's what it is. Now if you try to run the algorithm, now biggest is 4, biggest is 3, okay? Now we can't take this 1 because there's a 2 over here, right? So 2 is greater. 2 is the greatest out of all of these, right? So we just take 2. Okay, and now we have 1, 1. We just take those. So if you look at it, this is the same thing, right? What does that mean? That means that when we move the 3 up, right, that doesn't really do much. Okay, that didn't really do much. So is there a better way? Is there a better swap that can actually do something? Well, you'll look back at the test. You'll look back at the output, and you can see that 4, 3, 2, 1, 1, right? Third test case doesn't need to perform any operations. Oh, okay. Well, there's nothing we can do here, right? We already put the 3 up. Nothing happened, right? This is why USACO is trying to trick you, right? Because right now, after 2 examples, you probably be thinking, oh well, all I need to do is move whatever is the greatest up to the greatest spot, and then I'll have my right answer, right? USACO is purposely not giving you another test case that proves that this kind of algorithm doesn't work. And so that's why you need to be careful. And so I'm going to create a test case right now to show you how this problem is tricky and why this kind of just like assuming doesn't work. Okay, so I've went ahead and created a test case where this would fail. So in this case, right? If we just let's just run the algorithm. Let's just run the algorithm without anything. So we run the algorithm. The first thing we're gonna pick is 5. Go down the line. Okay, our greatest is 4 clearly, so we're gonna pick 4. Okay, go down the line. 2, 3, 1. What is the greatest? 3. We take that. Okay, anything else? Okay, 1. This is what we get. 5, 4, 3, 1. This is the best we can get. So now let's try to swap something. Let's try to move something to the front. And so you would probably think, right? Let's move the 4 right here. Okay, it seems pretty good, right? Seems pretty good. Move the 4 right here. Now we have 5, 4, 2, 1, 1, 2, 3, 1. So now let's run the algorithm again over here. So we will obviously take 5, obviously take 4. And now if we look, all of this stuff, the biggest is 3. We just take 3. Okay, we have another 1, we take 1. Oh, looks like it's the same again. So is this our final answer? No, it's not. There's a little trick here that you can do to get an even better result than 5, 4, 3, 1. So the thing is right over here. It's right over here. Okay, is this 2, 3 over here. What you can do is instead of moving the 4 and doing basically nothing, you can just move the 3 in front of the 2. And what you would get is the 3, 2, 1. So let's try that. So 5, 2, 1, 1, 4, and then we're going to move this 3 over here. So that's going to be 3, 2, 1. Okay, run our algorithm. 5, go. Okay, 4 is the biggest, 3 is the biggest, 2 is the biggest, 1 is the biggest. So 4, 3, 2, 1 comparing to 5, 4, 3, 2, 1 comparing to 5, 4, 3, 1. Right, 5, 4, 3, 2, 1 is gonna be lexicographically greater because you can see this 2 is greater than the 1. Okay, so what happened here? Why when we switch like a smaller number, right? When we switch a smaller number to the front, it actually did something. Okay, so now we need to think more. So what really happened here? So let's think. Let's go back. How does switching something ever help? Right? How does switching something help? Well, what happened before the switching is that we ignored all of these numbers, right? So the first thing in this case we're going to take is 6. So we ignored all of these numbers. We can't take them. And then we took 6, okay? So that's why when we put the 6 here, what we can do is we can now not ignore them, right? We can now choose one of these numbers maybe to take, right? So in this case, we took 5. That's good. So now we look at this, right? If we switch the 3 to the front over here, what it allows is that it allows us to not skip the 1. So we can consider 1. But considering 1 doesn't matter because there's already a 2, right? So we're going to ignore the 1 anyways. So that's why putting the 3 here doesn't work. Same thing right here. Exact same thing. When we put the 4 here, we don't skip the 2, 1, 1, right? So if we don't skip the 2, 1, 1, we can consider them. But even if we consider them, we're not going to take them because we're going to take this 3 over here. So that's why switching the 4 over here does nothing. So now let's look at the 2 and 3. Why does the 2 and 3 do something? Well, when we simply switch the 3 over here, we can see that we can reconsider 2 as an option. And 2 is an option. Why is it an option? Because everything after 3, right, is all less than 2. So that's why when we switch 3 in front of 2, we can see that now we can just take 2 because 2 is the greatest here. So now the thing becomes, right, when we switch something in front, we're actually not ignoring the numbers in between. And if anything in this region in between has a pretty big number, right? Pretty big as in bigger than whatever is after this number, then we can take it. And so with this algorithm in mind, it's a much stronger algorithm. It's just basically an add-on to the previous algorithm that we made. But this is much stronger, and when we use this algorithm, right, we're gonna pass all the cases because it's correct, right? So specifically, what should we do? Let's recap. All we need to do is every single time we're trying to look for the greatest number. Okay, so let me write this down real quick. Okay, so look for the greatest number. So now what's the second thing that we should do? So we should check the biggest in between numbers with the biggest after this number. What does that mean? That means when we're looking for 6, right? We find 6. The in between numbers are these numbers, and the after numbers are these numbers, right? So we're gonna check if there's anything bigger or equal to the set of numbers in here, right? So the biggest here is 5. The biggest here is 4. So that means there's something bigger, so that means we should switch this up. When we switch this up, it would do something, okay? So check the biggest in between numbers with the biggest after the number. If bigger, if in between has bigger, then we can switch, right? Then we can switch the 6 up. Okay, now what happens if not? If not, if not, well, that's what happens here, right? The 2-on-1 and the 2-3-1, the in between is smaller than the after. So if not, what we can just do is just ignore it, because when we switch it, it doesn't do anything. If not, ignore, and now look for the next biggest number and do the same, right? And we do the same. So after 4, the next biggest number is going to be 3, right? Now 3, the in between numbers is just 2, and the after number is 1. So 2 is bigger than 1, which means that we can use 2, and we find something that we can use, we're done. So why, when we find something we can use, we're done, right? What if we find many places where you can swap and something better would happen? Well, we come back to the lexicographically greatest, and we come back to this definition of, the first position I, where SI is bigger than TI, which means that we only care about the first position, right, being bigger. So that means the first time we find something that can help us create a better sequence, we have to take that, right? If we take anything later, that means it's going to happen later in the sequence. And lexicographically bigger means that something that is happening earlier in the sequence matters more than something happening later in the sequence. Right before we look at the code, there's another thing here, is that if we just do this, if we just check for the biggest just by cycling through, we're going to time out, right? Because that's a lot of numbers that you can check, and if you think about it, you're actually rechecking a lot of numbers, right? So in order to avoid that, what we can do is we can do a prefix sum, or in this case a postfix sum, but we can just call it prefix. We're gonna do a prefix sum, right, of the biggest. So we keep track of biggest, but it's not prefix because we're going this way. So this would keep track of the biggest here, the biggest in this range, the biggest in this range, the biggest in this range, the biggest in this range. And we can do this all in O of n, right? Because we can just cycle through from the back to the front, right? And then we can just keep track of the biggest, and we can put it in this prefix sum over here, right? And every single time we need to check what's the biggest after this. All right, all you need to do is you can take this prefix sum and just ask the prefix sum, all right, what's the biggest after I? So that is the final step that you have to do. And yeah, let's look at the code now. So, okay, starting off, we have t-test cases. We go in, we read the cows. Read the cows. Now we're gonna go and we're gonna check the biggest containing after this one. So that is our prefix, or like postfix sum, or not even sum, just biggest. So in this case, we're gonna cycle from back to the front. I'm gonna say M is our max, current max, and then we're gonna just max it with the current one, and all we're gonna say is all we're gonna do is put it as the current position, put max as the current position. So now we have a postfix biggest sum. So now we look through, and then we see we have start and current. So start is gonna be like the biggest, the big number that we're finding, and then current is just whatever number we're on. So as you can see, the start is -1 because, well, because we don't know if it can't be 0, because if it's 0 index is not always, the first number is not always the start, like the biggest number of all the sequence. So that's why we have it as -1. So while start is smaller than n-1, right, we're gonna have our b big. So b big is gonna be in between big, so right. So it's gonna check all the numbers in between as we cycle through them, and it's gonna max itself with this number. So it's gonna give us the biggest in between. And we have this while loop here. We have the current cow is not equal to the big, right? So when we haven't found the big yet, we're just gonna keep cycling, and we're gonna update this b big, this between big. So now over here we found it. So after we find it, we're gonna check if the b big is bigger than the big after this current, right? This current is now the thing that we found. So let's just check if the in between is bigger than whatever's after the current. If it is bigger, that means we found something. We can use it. All we need to do is just move this cow to whatever our start is, right? So in order to do that, I put a temporary variable, and then we're gonna say cow's current, and then we're just gonna first erase the element at position current, and then we're just gonna add it to right after the start, okay? And we're gonna add temp. Okay, and then we're done. If we haven't found it, just gonna do it again. We're gonna put the start as the current, and then current add. Okay. So now over here, now our cows should be formatted in a way where if we had something to swap, we would have swapped it, right? And if we didn't have anything to do, we would have kept it the same. So now we're just trying to reconstruct, and we're just trying to get the answer here. So this should be pretty simple. So I'm going to reuse the variable m here, cycling again from the back to the front, and now we're going to just update everything, right? We're just going to update the big, right? The prefix somewhere over here, right? We're just going to go and update it because we might have switched something, and then we just update it. We need that because now we're going to actually calculate, or we're going to run our algorithm that we talked about before. So we're going to say our result, and then we're going to say our big is the current 0. Okay, so now we're going to check if the cow's eye is the big, is the current big that we're looking for, right? If it is the biggest we're looking for, okay, yeah, we just put it in, and now the biggest we're looking for is whatever the biggest after that is, so that's big I plus 1. Over here, we just start printing out the response, and make sure you don't print out a space at the end. To do that, I'm going to cycle to the size -1, and then we're not going to print a space. We're going to print a new line when we reach the last element. And that's it for this problem. I hope you guys enjoyed. This problem shows that USACO likes to trick you with the test cases, so please be careful when you're trying to come up with an algorithm, and make sure it works. Make sure it works. Test it with your own cases first, and then implement it, because you're gonna waste a lot of time if you come up with like a wrong solution. You spend that much time coming up with a wrong solution and coding it, and realizing that it's actually the wrong solution, right? So good luck to you guys. I'll see you guys in the next USACO video.